Hello, at this part I'm going to teach you about the Serial Peripheral Interface, the SPI, on the STM32 board. And on the SPI, we're going to look at the GPIO configuration and the SPI setup, and then we'll do the transmit and receive functions. In our demo, in our starter kit, we have an SPI module. We've got the RFID RC522 RFID module, and this one interface with the board using SPI, and we can take a look at the exact pinouts that this one is mapped to. This one, the RFID has got these important pins. The reset pin, I think, is we've got the chip select, the serial clock, and the master output slave input, and then the master input slave output. So those are these are the important pins for the SPI configuration, and there are basically four pins overall, the important ones, and the others are mapped to, so the RST pin is obsolete. I've just connected this one to 3.3 volts so that it will always be disabled. Okay, so these are the physical wiring, and we are going to first get our SPI ready. We're going to set up the GPIO configuration, and then the SPI peripheral configuration, and then finally we'll do the SPI transmit and receive. And this part, we are only going to test SPI, and after that, we're going to integrate the RC522 RFID module library. I've already created this library beforehand, and its purpose is just to interface with SPI to kind of detect RFID tags. So like the one you see on my webcam, so this is an RFID tag, and the same as this card as well. So both work. Okay. Now, so let me begin by doing the basic cleanup to our currently existing code, and we're going to go ahead and add our SPI header and source files and the library, and I'll show you exactly step by step how we program SPI peripheral on the STM MCU. Alright, so let's begin. Now, in our code, I'm going to close the unnecessary files to start with. I'll keep my main. As usual, the first step, if we have a newly added peripheral, is to add its header and source file. Okay, since we don't have any SPI, let's add one, and that all SPI configuration and functions is going to go into here. So we're going to call this spi.h, and as part of the source directory, we also need to do spi.c. Alright, now on the spi.h, we are going to add the basic functions. So they're going to be we'll have several functions here. The first and most important perhaps of them all is to configure the GPIO. So that's SPI GPIO pins setup. Without that, none of the SPI will work. So that's the first step, and we're going to call this function SPI GPIO config. So that's particularly for setting up PA, our GPIO pins that we just saw in the manual, on the starter kit manual, like the pinout manual, where we need to set up our chip select pin to be a normal output on PA4. We need to have our SPI on PA5, PA6, and PA7. And that's a spoiler, it's going to be SPI1. Okay, now let's not forget, at the very beginning of SPI.h, we need to include our main. Right, so that's main.h. Now, the other function required is to do the SPI normal peripheral configuration. Okay, so that's similar to the above, but this is not for the GPIO. This is just purely for our SPI peripheral, where we're going to look at SPI registers. So I might as well just show you those now. maybe we just head to that SPI section. So that's going to be section 25, all right, where we're going to program those SPI registers. Excellent. Now, this is the function, and then the other function prototype that we're going to add is SPI, then transmit and receive. Okay, we really got to that. So that's going to be SPI transmit, and after that SPI receive, and we're going to do those in polling mode all the times. Okay, so that's going to be transmit. And now for SPI transmit, I'd like it to return a Boolean status. So that's to determine whether the operation is successful or it was a failure. Okay. Now the first parameter this function require is a pointer to the data buffer. So that's going to be a pointer to data, and the other parameter, the next one, is the length, and finally the timeout. And similarly for receive function, it would have very similar structure. It's gonna, just the name is different, but everything else is the same. And next we are going to, now we finish with the normal SPI peripheral transmit and receive. Now I'm going to do some specific RFID module thing, and that's something concerning the chip select. Okay, because that's another SPI peripheral thing. Now for this board we have the chip select, for this module the RFID module, as I just mentioned earlier. PA4 is going to be the chip select. So I'd like to have the chip select also part of the SPI header file, okay, just to keep things consistent. I could have added to the GPI U.HNC, but I like to keep it in here just to put all SPI related in the same page. Okay, so that's going to be my RFID module, chip select pin configuration. And then after the configuration, I'd need to control that chip select. So that's going to be chip select set or reset. This is the right function. Okay, so I'm going to call this SPI chip select, or perhaps RFID chip select config, because that chip select belongs to that RFID module. That's why I like to use this one. And then the set reset function, perhaps I can call this chip select right, so to determine whether it's set or reset, and that will take a Boolean state. Okay, so that's pretty much it. These are all the function prototypes we need. Now let's go ahead in the SPI source file and define what each does. Okay, some of them will be relatively easy, and some others would require some rigorous kind of referral to the reference manual and back and forth to ensure we catch the right requirements for that function. So anyway, so that's going to be SPI.h. I need to include that header file. Now we are going to begin with the first function. The first function, the objective in here is to set the SPI pins to have them as going to be PA5, 6, and 7, and we need to have those. We'd like to have those depending on their mode. So serial clock is always going to be output. Master output, MOSI is going to be an output as well, whereas meso pin, which is PA6, needs to be an input. Okay, and finally we're going to verify the peripheral remap, and we might as well do the remap, the very first one. Okay, so let's do the remap first, which is to ensure PA5, 6, and 7 are SPI1 and are mapped to the correct pin. And after that we need to do PA5 and PA7, which are the clock and MOSI. Okay, and those are outputs. Clock is provided by the master, which is the STM, so that's going to be an output. And then we need to set up our PA6, and that's the master inputs, and we need to have that as input. Okay, that's pretty much everything we need to do. Now, for the remap, I'm first going to verify that from the remap registers. You might already be familiar with the steps we need to take. So that's, we need to go to SPI remapping function. So that we expect it to be, yeah, SPI1. So SPI1 clock Mizu Muzi, when the remap is default to 0, they're going to be BA5, 6, and 7. If we have a remap, then it's going to be BB3, 4, and 5. So therefore, it seems like we don't really need a remap because they're already, SPI1 is already mapped to 0. And that should be the default one. If it didn't work, then we know we might need to do that anyway. But for now, I'll leave it. I'm not going to do a remap because it seems unnecessary. All right, that's good. Now, the first step is to enable port A clock. So let me do that. So that's going to be RCC app clock 2. And that we are going to set some bit field. Therefore, we'll use this macro or define. That's going to be IO port A. All right, let's just double check we had everything correct. Let's verify that. Okay, it seems like I need just to save. That's good. All right, ENR, and that's port A that I'm looking for. All right, excellent. That should enable port A clock for us. Okay. Perfect. Now, for the serial clock and master output, we need to have those set to output mode and set it to alternate function push pull. So therefore, that's going to be equivalent to, if we can head to the GPIO registers, that will be, we have the mode configuration and that of the configuration thing. Okay, and since those are 5 to 7, that's going to be in the low register always. Okay, so in order to set 5 mode, we need to have the mode to be output with perhaps, we need to select one of the speeds. We might as well choose the medium speed, which is 10 megahertz. And then we need the configuration to be set to alternate function push pull. All right, so therefore, this one needs to be 0, 1, and that's need to be 1, 0. Okay, so let's keep that in mind. Okay, now, so that's going to be first, let's do the mode. It's going to be the low control register. I first need to clear those bit field because I'm going to set them to a specific value. So we're going to say GPIO CRL, that's going to be mode, pin number 5 for the clock. And also I'm going to do them all in the same instruction, and then pin number 7. So we need to clear both of them, and sure enough, that's 3 shifted by 20, 3 shifted by 28. Excellent. And then after that, we need to do the so now we have to set the mode to whatever value you like. Therefore, that's going to be set bit field, and I want the mode to be for both of them to be 0, 1. Therefore, that's going to be this bit field, right? Let's just double check. So we like for the mode, we need that to be this one only. Okay, therefore that's the correct setting. Excellent. Now we need to do the configuration. Okay, so this particular one was for mode to be output with speed 10 megahertz. And then here we need the type of output to be alternate function push pull. In order to achieve that, we're first going to clear those bit field as well. So I'll use the same statement, but instead of mode 5, that's going to be CNF5 this time. And same thing for this one. Instead of mode 7, that's going to be CNF7. Excellent. And now, in order to set alternate function push pull, it is 1, 0 this time. Therefore, we're going to do bit field number 1 this particular time. Okay. So we are setting bit field at this particular step, and we want bit field number 1 to be high. All right, excellent. So this is done. PA5 and 7 are finished. We have set the mode to be output with the speed required and the particular type to be alternate with push-pull. Now let's do PA6. This one also is relatively straightforward. That will take on very similar output mode. So for this one, it would be input mode, and we want it to be floating input. Okay, so it will have the same statement as the above. We just need to clear it basically, but no need for 5 and 7. It's just going to be 6 now. Let me just show you how that looks like. So we like the mode to be input, therefore we need to clear the mode bit field for number 6, and that's what we've done. Now, in order to do floating input, we need to set 0, 1, and therefore we have to reset those for number 6 first of all. That'll be number 6, and no need for 7 anymore. And after that, we are going to set that particular required bit field only, which is 0, 1, and therefore that will be bit number 0 that needs to be high only. And that's it. That's everything. We have now set up PA5, 6, and 7. So 5 and 7 to be output, and PA6 to be input for our master input slave output. And that's pretty much everything on the GPIO configuration. All right. Excellent. Now, for our SPI configuration, however, that's for the peripheral, and I like to go slightly slower in here because that's an advanced thing. You need to be slightly familiar with SPI to know all the parameters. But let me give you a quick walk through the main parameters that we're going to set up. So I'm going to head to the SPI peripheral, where we're going to sorry, I can't seem to see SPI anymore. Yep, that's the one. So I'm going to head to SPI registers, specifically the control register. So we have parameter like the direction, data format, and we've got baud rate, definitely master selection, clock polarity, clock phase, and something related to interrupt. So I'm going to list them out, all the configurations. So we need to enable SPI clock first of all, and after that we need to set clock phase and clock polarity. So these are the essential hardware level, or kind of the essential timing requirement of SPI. So we need to set the clock phase and the clock polarity. We need to set the mode, basically either master or slave, but it's certainly going to be master in our case. We need to set the baud rate, so that's how fast SPI clock is. And then we need to do we need to select the type of transfer, so that will come to that. That will be MSB first. And then we need to select the duplex, so that will be full duplex in most cases. We need to do a data format, so do you want 8 bits or 16-bit transfer? In our case it will be 8, and we need to specify whether we have hardware slave select or software. In our case it will be a software slave select, because we're going to manage the chip select ourselves. And then finally we need to enable SPI and clear all flags. Alright, so these are going to be the logical steps to follow. Now let's go ahead and replace each one with its equivalent programming statement. Now, the very first one, in order to enable SPI clock, let's search and find out which clock is the main source for SPI. And I believe that should be either APP1 or APP2. Let's take a look at both of them. The APP1 has timers, it has SPI2 and 3, but it doesn't seem to have SPI1. Let's take a look at the other one. This one has some ports, and indeed it has SPI1, and therefore that's the one we need to use. Okay, so that's going to be APP2, very similar to the port enabled clock, but this time we are enabling SPI1. Perfect. Now for clock phase, let's first find out which SPI register is responsible for clock phase selection. Okay, I'm gonna scroll down slightly. We'll take a look. Yep, it's control register number 1. So here's the clock phase, and usually an ideal it's usually you want to do on the second clock transition is the first data capture edge, so that will be on the rising edge or something like that. So these are, I'm used to setting them by default to second transition, and also clock to be high when idle. Okay, so these are kind of the default SPI settings, but in some application you might want to change them, but usually it will remain like this all the times. Okay, so clock phase excuse me, so clock phase needs to be high, and therefore that will be SPI1 control register number 1. We're going to set some bit fields, and that will be our clock phase. Okay, excellent. And then the same thing going to be for clock polarity. It's going to be, I think, C pole. Yep, we need to set that high. And then for the mode, we definitely going to have the SDM to be in master mode. This one is also part of control register number 1. Let's scroll up. Yep, it's the master selection. Let's do that. So I'll do the same statement, but it's not going to be for this. It's going to be for the master mode. Excellent. And after that will be the baud rate, and according to the control register number 1, a baud rate is so that depending on the clock that is clocking SPI peripheral, we can determine either a clock is divided by 2, 4, 8, 16, 32, and so on and so forth. And now a very start safe point is to go below 1 megahertz, just to 1 or below 1 megahertz, to have a very basic test. If you think your device can manage higher speeds, all right, then go higher. But the very beginning, I know that my SPI ABP2 clock is ticking at 72 megahertz initially. So 72 megahertz, I'll divide that by like 100 or something. So divided by 128, that will get me 0.5 megahertz, 0.5 or something megahertz. I think that's good enough. So I'd like to select baud rate to be 128, the baud rate prescaler. All right. So I need to set this baud rate register to 011. So let's do that. Okay. So that's still part of the same control register number 1, and therefore that's gonna be, I first need to clear those bit fields. So I need to clear the baud rate bit fields. What's that called here? It's the BR. Okay, that's good. So this needs to be cleared first of all. Okay, and then I'm going to set the required bit field high only. Okay, so we are setting a bit field, and we might be setting more than one. We're going to set a bit field number 1 and also bit field number 2. Let's just verify that. Yep, so 128 is bit field 1 and 2. That needs to be high. Brilliant. Now for the MSB, so that's to determine which one is first, the MSB or the LSB. I'm going to say this is MSB first in most applications, including this module. So therefore that needs to be reset to 0, this bit field. Okay, so we're going to reset something in control register number 1. So we'll use this statement, but it's going to be the LSB first bit field that we're going to reset. All right, that's good. We're really more than halfway through, and that's really good. Now for the mode, we are going to have full duplex, and according to the manual, there is a bit field for RX only. We're not only receiving, we're also transmitting data. Therefore, it's going to be full duplex. So this RX only bit needs to be reset to 0. So I'll use the same reset statement, but replace LSB first with RX only. Excellent. Now for the data format, this is also apparently part of control register number 1. It's a very rich register apparently. So that's the let's try to find that out. Yep, so that's the data frame format. and we're gonna send byte by byte, so therefore it's gonna be 8-bit data frame format, and therefore this bit field needs to be reset to 0 as well. Okay, so it's gonna be the DFF thing. Yep. Now the last three things, we need to determine the slave select. Let's look at that and try to find out what is it that we need to do with the slave select. Okay, so we've got two options for a slave select. So that's to do with software slave management. Software slave management is disabled or enabled when SM bit is set, NSS bin input is replaced with the value of this bit. No, so we'd like to disable that. And also this is just to control the internal slave select, and therefore only when this one is set, the value of this bit is forced into so on. Nope, I don't want that, so I will reset both of them to 0. Okay, so that's going to be another reset bit field. Now, just a side note here, those might really be reset by default, but it's a good practice in this particular case to do them again, just in case. I just like to do that in some cases, not in all cases, of course. Okay, now finally we need to enable our SPI and then clear the initial flags. And to enable SPI, this is control register number 1, we need to set some bit field, and that's clearly, you would see that very clearly in control register number 1, it's the SP enable bit. There we go, this is bit number 6. Okay, so that would be SP enable bit field. Excellent. And now in order to clear all the initial flags, we need to read the SPI status register, and according to the manual, I think that should be stated very clearly. In order to clear that bit field, we need to read the status register. Okay, this is by the software sequence, and according to that should be okay, to clear this bit, access to this, and then write to control register number 1 and so on. Okay, so the easiest way is that we need to just make a read from status register, and I'm going to do that with a volatile variable to avoid the compiler optimizing that variable and this statement basically. Alright, excellent, and that's it. This is everything. This is how we set up SPI GPIO and the SPI peripheral. Now we're going to carry on and do the SPI transmit, receive, and the RFID chip select functions.